Good morning. Today we will revise 26 rearrangements at a glance. First, pinacol pinacolone rearrangement. It is actually the झलक दिखलाजा कार्यक्रम. झलक दिखलाजा. You will see the झलक. You will see the replay of 26 rearrangements. First is pinacol pinacolone rearrangement. It is R1, R2, R3, R4. OH, OH1, 2 diol. It is pinacol. When it is heated with acid, you will get pinacolone. Here H plus will get attached with this OH, resulting in OH2 plus. Suppose H plus comes here, OH2 plus. And now water will be eliminated from here and it will be carbocation. Now question arises, which OH is eliminated, whether this or this? Then you have to decide, you have to solve this question from the stability of carbocation. That carbocation is formed which is more stable. Okay? Now it will rearrange in this fashion, leading to R1 C OH C R3 R4 and it is R2. It is R2 and positive charge will be here. Now second question arises here, whether this R1 will rearrange or this R2 will rearrange. Then you have to decide on the basis of, friends, the group having more electron density will migrate first, and for this a trick is हमारा प्यारा राज्य. Order of migration, migratory aptitude is this. It has the most migratory aptitude. Second is phenyl and third is alkyne. Now what will happen? This, and you will get R1 C double bond O C R3 R4 R2. This is pinacolone. Number 2, semipinacolone rearrangement. Suppose it is TS, one is OH and another is TS. TS means tosyl group. Tosyl group is very good living group. So it doesn't matter here that whether this will be eliminated or this will be eliminated. No, surely it will be eliminated, leading to, when it is heated, leading to this. Okay, and then either this or this, depending upon हमारा प्यारा राज्य, that will rearrange and you will get pinacolone. Just discussed above mechanism, just discussed in pinacol pinacolone rearrangement, that mechanism is also applicable here. Okay, if NH2 is here and when it is diazotized, you will get this diazonium salt. Then it will be eliminated, resulting in positive charge here. And in the similar fashion, just like pinacol pinacolone rearrangement will take place. Third is dienone phenol rearrangement. It is diene and it is dienone. RR, when it is heated with H plus acid, H plus will come here and OH double bond OH plus. Now RR, it will come here, it will come here. It is OH RR, positive charge is here. It is 2 degree carbocation, and now it rearranges in this fashion. You will get OH R is here. It is 3 degree carbocation. It is 3 degree carbocation. Okay. Now it is 3 degree carbocation. Now what will happen? What will happen? Hydrogen is here. Here suppose. It will come here. Okay. Hydrogen is here. Okay. And when it will come here, double bond will be here, double bond will be here. And each hydrogen now will come here, this bond, and you will get this OH R this. It is dienone phenol rearrangement. It is just reverse of pinacol pinacolone rearrangement. You are getting here 3 4 1 2 3 4 3 4 disubstituted phenol, and you are getting this from dienone, so it is called dienone phenol rearrangement. Number 4, Wagner meerwein rearrangement. Here we will change the carbon skeleton. Suppose it is carbon skeleton, it is converted into this. Suppose it is neopentyl bromide. When it is heated with base, this bromine is eliminated as bromide ion. Positive charge here. Positive charge here. Now it is 1 degree carbocation. It will rearrange in this fashion. CS3, CS3, CS2, CS3. It is 3 degree carbocation. Now here there are two possibilities. First one is even reaction, double bond, this hydrogen will be eliminated and you will get CS3, CS3, double bond, CH, CS3. It is even. Now it is even. It is SN1. OH minus, you have base here, you have taken base. OH minus will come here and you will get CS3, CS3, OH, CS2, CS3. You will get this alcohol in this fashion. Here you have to remember that in Wagner meerwein rearrangement, carbon skeleton is changed. And I have made a trick for Wagner meerwein and wolff rearrangement. For Wagner meerwein, बैगन आर में आएंगे, कार्बन स्केलेटन को बदलेंगे. बैगन आर में आएंगे, कार्बन स्केलेटन को बदलेंगे. भेड़िया को पुचकारेंगे, डायजोकीटोन से कीटीन बनाएंगे. फॉर वुल्फ रिएरेंजमेंट. ओके, आई विल टेल यू इट अगेन. Friend, here one thing is also important to underline that if OH group is here, the Wagner meerwein rearrangement can be taken place in presence of acid. H plus will come here and now this bond will break in this fashion, and now you can solve the problem, you can write the mechanism in this case. Number 5, conversion of diazoketone. Conversion of diazoketone. CH3, C double bond O, CHN2. Conversion of diazoketone. into ketene CH3 bond CH3 bond C H CH. Actually this CH3 will come here. N2 is eliminated. This CH3 will come here. CH3 CH double bond C double bond O. It is ketene. Diazoketone. Conversion of diazoketone into ketene in presence of solid silver oxide is known as Wolff rearrangement. Now we will see its mechanism. Right here, not CH3 but R in general. R C double bond O CH minus N triple bond N plus. Nitrogen gas is eliminated in presence of whole the reaction is carried out in presence of silver oxide, solid silver oxide. R C double bond O CH. This is carbene. Nitrogen gas is eliminated. Now it will come here, resulting in R will come here. R CH double bond C double bond O. It is ketene. It is the Wolff rearrangement. If the rearrangement is carried out in presence of water, then water H2O, then what will happen? This bond will break. OH will come here, H will come here. R CH2 C double bond O OH. It is undisturbed synthesis. Actually, undisturbed synthesis is conversion of a carboxylic acid into its higher homolar. Suppose it is RC-OH. When it is treated with thionyl chloride, you will get acyl chloride. Okay? When it is treated with diazomethane, CH2N2, you will get RCON2. When it is heated with solid silver oxide, you will get ketene, RCH double bond C double bond O, ketene. When it is treated with water, means the reaction, if reaction is carried out in water solvent, then you will get RCH2 C double OH. So, conversion of carboxylic acid into its higher homolar is known as undisturbed synthesis. This is all about Wolff rearrangement and undisturbed synthesis. So, we have made a trick to remember, to learn the reaction Wagner-Meerwein rearrangement and Wolff rearrangement. In Wagner-Meerwein rearrangement, carbon skeleton is changed, and in Wolff rearrangement, diazoketone is converted into ketene. So I have made a trick. वैगन आर में आएंगे, गाड़ी है 4 चक्का, वैगन आर में आएंगे, कार्बन स्केलेटन को बदलेंगे. वैगन आर में आएंगे, कार्बन स्केलेटन को बदलेंगे, भेड़िया को पुचकारेंगे. वुल्फ मीन्स भेड़िया. फॉर दिस, भेड़िया को पुचकारेंगे, डायजोकीटोन से केटीन बनाएंगे. 1-2 migration of it is NH2. Actually, 1-2 migration in carbocation obtained by diazonium salt is known as demjanov rearrangement. It is diazotized. By diazotization, you will get N2 plus. Okay? And when nitrogen gas is eliminated, you will get this. And due to this positive charge, this bond will shift here and you will get this. And this bond, this. Okay, this carbon is this. and now positive charge will be here. When in presence of water, you will get this. It is actually, this is the carbon, you will get this alcohol. And it is the three-membered ring, yet it is very much stable due to dancing resonance. And in the whole reaction, what happened? What happened? Four-membered ring has converted into three-membered ring. It is ring contraction. In the similar fashion, you can see ring extension. Suppose it is amine. On diazotization, you will get this. You will get this. And when this nitrogen is evolved, you will get this positive charge. You will get this. And due to this bond will shift in this fashion, and you will get five-membered ring. You will get five-membered ring, and positive charge will be here. And this carbon is this. Now there is positive charge is no longer here. This carbon is this. Rather positive charge will be here. In presence of water, you will get this. It is ring expansion. Overall, you have seen that four-membered ring has changed into five-membered ring. Thus, by demjanov rearrangement, you can carry out ring expansion or ring contraction. Number 7. Demjanov rearrangement. Actually, it is the extension of demjanov rearrangement. Here, it is cyclohexanon and it is cycloheptanone. Conversion of cyclohexanon into cycloheptanone can be carried out by tiffene demjanov. It is cyclohexanon. When it is allowed to react with nitromethane, carbon-hydrogen bond will break and this pi bond will break. Hydrogen will come here and the rest residue will come here. OH, and here it is CH2NO2. It is allowed to react with SnHCl. SnHCl is a very good reagent for reduction of nitro group, and you will get CH2NH2. When it is diazotization, you will get OH, CH2N2, N2 plus, diazonium salt. This nitrogen gas is eliminated from here and you will get CH2O plus. Now this bond will break and gets attached with this carbon and positive charge will be developed here. So now it will be 7-membered ring. 7-membered ring, and it is OH and positive charge will be here and nothing else. And due to this positive charge, this bond will break in this fashion and you will get cycloheptanone minus H plus. Cycloheptanone. When benzil is heated with base, it is pH, it is pH. When benzene is heated with base, you will get benzilic acid. This pH will come here, pH, CpH. This pH will come here. This O is converted into OH and it is C double bond O and OH. It is benzilic acid, and moreover if you are taking sodium hydroxide, you will get sodium salt of benzilic acid. Now let us see its mechanism. What will happen? Suppose this nucleophile is attacking in this fashion, pH, C double bond O, C. When it attacks in this fashion, then this bond will break in this fashion, O minus, OH, pH. And if this returns in this fashion, it will rearrange in this fashion, pH, CpH, double bond O, C, OH, double bond O. It is benzilic acid, and it is normally that when sodium hydroxide is used, you will get sodium salt of benzilic acid. Now we are going to teach you 4 rearrangements. High School Living Certificate, Hofmann, schdimdt, lossen and curtius. In all these 4 rearrangements, intermediate is nitrine, and when the reactant is treated with different and specified reagent, you will get isocyanate, and when it is hydrolyzed, you will get primary amine. So we will see one by one. First is Hofmann rearrangement. When amide is heated with bromine and caustic potash, amine is obtained. What will be its mechanism? It is amide, bromine reacts with it, leading to this NHBr. Okay? This hydrogen is acidic, so in presence of base, this hydrogen is eliminated. So you will get RC double bond O N minus Br. This Br is eliminated as Br minus RC double bond O, and it is nitrine. You are getting first nitrine. Okay? Now it will come here, and these are will arrange in this fashion. So you will get RM double bond C double bond O. It is isoalkyl isocyanate. Means first you are getting nitrine, it is nitrine, then it is converted into, it is very reactive species, so it gets converted into isocyanate by rearrangement. Now when the reaction is carried out in presence of water on hydrolysis, suppose actually this water will attack here, but in short, remember that these both bonds will break, 2 hydrogen will come here and oxygen will come here, and you will get primary amine plus CO2. It is all about the mechanism of Hofmann rearrangement. Number 10, schdimdt rearrangement. When carboxylic acid is heated with hydrozoic acid in presence of strong sulfuric acid, primary amine is formed. What will be its mechanism? It is carboxylic acid. Friends, you are taking 3 acids here, carboxylic acid, hydrozoic acid, sulfuric acid. So I call them three idiots, and these three idiots will combine together, leading to base primary amine RNS2. In presence of H plus will come here, and then water will be eliminated, leading to this carbocation. Now this hydrozoic acid will attack here, leading to this bond N, bond H, N triple bond N, it is plus. Now this bond will break in this fashion, nitrogen gas is eliminated, and you will get RC double bond O, N, H, positive charge is here, and this hydrogen will now leave this position, and you will get this. It is actually nitrene. Now rearrangement will take place. It will come here, and you will get R and double bond C double bond O. On hydrolysis, at this position RNH2, two hydrogen will come here, and one oxygen will come here plus CO2. Thus you are getting primary amine. Friends, in all the four rearrangements, high school living certificate, Hofmann rearrangement, schdimdt, lossen rearrangement, and curtius rearrangement, you will get nitrene and consequently isocyanate, and on hydrolysis it will produce primary amine. Number 11, lossen rearrangement. When hydrogenic acid RC double bond O, NHOH, hydrogenic acid, carboxylic acid, it is formed by reaction of carboxylic acid and hydroxyl amine. So it is called hydrogenic acid. It is heated with either acid or base. You will get primary amine. Now we will see its mechanism. Mechanism in presence of acid, and then mechanism in presence of base. First we see acid catalyzed mechanism. It is RC double bond O, NH, OH. In presence of acid, what will happen? H plus will come here, leading to OH2 plus. Okay? Now this bond will break. Then RC double bond O, NH, positive charge here. Okay? Now due to this positive charge, this hydrogen is released, and you will get RC double bond O, N. It is nitrene. Now rearrangement will take place. It will come here, and you will get R bond N double bond C isocyanate. When it is hydrolyzed, you will get hydrogen will come here, oxygen will come here, RNH2 plus CO2. Now we will see base catalyzed mechanism. It is hydrogenic acid. In presence of base, this base will abstract this hydrogen minus H2O, RC double bond O, N, OH. Now this OH is eliminated, and you will get this. This is nitrene, and now it will come here, rearrangement will take place. R and double bond C double bond O, when it is hydrolyzed, H2O, RNH2 plus CO2. This is the lossen rearrangement. 12 is curtius rearrangement. When azide is heated or exposed to light, what will happen? This bond will break and you get this nitrogen, okay, minus N2. Now it comes here and this R will rearrange in this fashion, leading to R and double bond C double bond O. It is actually nitrogen. Nitrogen turns into isocyanate, and on hydrolysis H2 will come here, O will come here, you will get amine plus carbon dioxide. Now we will see a trick to remember 4 rearrangements which have been taught before it. High school living certificate. Hofmann rearrangement, schdimdt rearrangement, lossen rearrangement, curtius rearrangement. In Hofmann rearrangement H, this amide is treated with bromine and KOH. You will get isocyanate. In all these 4 rearrangements, intermediate is isocyanate, and before this it remains as nitrogen. It changes into nitrogen changes into isocyanate in all these 4 rearrangements, and these isocyanate, when hydrolyzed with water, you will get primary amide and carbon dioxide. Okay, it is amide in Hofmann rearrangement. In schdimdt rearrangement, it is carboxylic acid, hydrozoic acid, and sulfuric acid. Again, I am repeating, to learn schdimdt reaction, it is a trick. I have said that all these 3 are acids, so I say these are 3 idiots. 3 idiots. All these 3, carboxylic acid, hydrozoic acid, sulfuric acid, and all the 3 acids will combine together, giving rise to amine, base. 3 acids will give base. Okay, it is lossen rearrangement. When hydrogenic acid is heated with either acid or base, you will get first cyanate, and then when it is hydrolyzed with water, you will get primary amine. In a similar fashion here, it is curtius rearrangement. When azide is heated or exposed to light, you will get isocyanate, and which upon hydrolysis you will get primary amine. When oxime of carbonyl compound C double bond NOH R1 R2, when oxime of carbonyl compound is heated with phosphorus pentachloride or acid, suppose it is OH and you are treating it with acid, H plus will come here leading to oxonium ion, and then that oxonium ion will be eliminated, will be released, leading to positive charge here. In the similar fashion, if you take PCl5, then OH is eliminated and chlorine will come. R1, R2, C double bond N, here. Chlorine is better leaving group. Chlorine is better leaving group. So chlorine may be eliminated easily. Actually, you should know that Beckmann rearrangement is trans rearrangement. Trans. So, friends, it will be eliminated and it will come here, and you will get R2C positive charge double bond N and here. Okay, it is trans elimination. This chlorine and this group is in transposition. Now H2O solvent, this lone pair of electron will attack here, and you will get R2C OH2 plus double bond N, sorry, not Cl, it will be R1, double bond and R1. Now H plus will be eliminated, minus H plus, and you will get R2C OH double bond and R1. It is in all, in and all. It will tautomerize in this fashion, R2C double bond O NH R. It is substituted R1. It is substituted amide. So when oxime of carbonyl compound is heated with phosphorus pentachloride or acid, you will get substituted amide. Number 14. Baeyer-villiger oxidation. When ketone is treated with hydrogen peroxide or perbenzoic acid or metachloroperbenzoic acid, we will get ester. Suppose it is ketone and methyl phenyl ketone and oxygen of per acid. Actually it is oxidation. It is rearrangement and also it is oxidation. And oxidation, oxygen of the reagent, oxidizing agent will be here. We will see it in mechanism. And this is phenyl, this is methyl, which will migrate. The migratory aptitude is हमारा प्यारा राज्य HPR. Hydrogen, highest migratory aptitude, then phenyl, then alkyl. Okay, so these phenyl will migrate. So oxygen of oxidizing agent will come here. Okay, not oxygen will come here, and you will get ester. How? First of all, you should know it is per acid. It is per acid, and when it will break from here, why break? These two oxygen atoms are highly electronegative, and electron pair, two electron pair are there. Due to repulsion, the bond will cleave easily. So, friend, sorry, we have to take per acid R1, 2, 3, 3 oxygen. It is per acid, and it will give this proton minus and H plus. Okay. Now suppose R1, R2, it is ketone, H plus, this H plus will come here at this place, R1, R2, C, OH, double bond OH, positive charge, it will come here, R1, R2, C, OH, positive charge. Now it acts as nucleophile. This minus RC double bond O minus, it will attack here, and you will get R1, R2, C, OH, O, C double bond O, R. Okay, you will get this. Now here we have to underline that it is carbocation, electron deficient carbon. But Baeyer-villiger oxidation is the only rearrangement we are looking at, which involves electron deficient oxygen. So it will break in this fashion, and RCOO minus will be eliminated, will be released, and you will get R1, R2, COH, and here it is O positive charge. Okay, it is electron deficient oxygen. It is the only rearrangement which involves electron deficient oxygen. Now migratory aptitude is seen here. Here R1, R2, you have to see that which group has more migratory aptitude. decide according to this. Suppose it will come here, then you will get R1C OH, positive charge is here, O R2. Now it is, this bond will break in this fashion and you will get R1 C double bond O, okay, double bond O R2, and this hydrogen is eliminated, is released as H plus, H proton. You will get this ester, okay. Number 15, it is naber rearrangement. Friends, now we will see rearrangement involving carbon rich intermediate. Carbon rich intermediate means carbanion will be the intermediate. And three types, Narendra फिर से, it is three. Narendra फिर से means Narendra Modi फिर से. N stands for naber rearrangement, F stands for favorskii rearrangement, and S stands for shapiro rearrangement. Okay, one by one we will see them. First, naber rearrangement. It is oxime tosylate. Suppose it is R dash or R1. Okay, it is oxime tosylate. When it is treated with base ethoxide, we will get alpha amino ketone. Okay, let us see its mechanism. This base will extract this hydrogen and you will get RCH minus C double bond N OTS bond R1. Now it will attack on it with releasing of tosylate anion. Okay, and it is RCH C double bond N R1. It is three-membered ring. Now question arises, this solvent, it will act as nucleophile. This lone pair of electron will attack at this carbon, not at this carbon, because it is double bond and nitrogen is here. Due to this double bond and nitrogen is also here, but due to this double bond it has more delta plus than this. Due to this delta plus, this nucleophile will attack here. So you would have RCH C OH2 plus and it is N minus R1, and H plus will be released from here, and so RCH COH NH R1. Now this bond will break in this fashion and this bond will break in this fashion, and you will get RCH NH2 will be here, C double bond O R1. It is alpha amino, it is main group and it is alpha position with respect to this, so it is alpha amino ketone. Okay, when oxime tosylate is treated with base, heated with base like ethoxide, you will get alpha amino ketone. Friends, number 16, favorskii rearrangement. Narendra फिर से naber rearrangement, favorskii rearrangement and shapiro rearrangement. Okay, this is favorskii rearrangement. When alpha haloketone is heated with base like sodium ethoxide and ethyl alcohol. If you take sodium ethoxide, the solvent will be ethyl alcohol. If you take sodium methoxide, solvent will be methyl alcohol. Okay. This base will ethoxide ion. This base will extract this hydrogen. Why not this hydrogen? Carbon ion, if friends suppose it is carbon ion. Again I am repeating that favorskii rearrangement also involves electron rich intermediate, that is carbon ion, like naber rearrangement. Okay. This negative charge is stabilized by resonance. It will come here, it will come here. If minus charge would be here, then it will also be stabilized by resonance. But this negative charge will be attracted, lowered. Density of this negative charge will be lowered by the electron attracting group, that is chlorine group. So this carbon ion will be more stable. Now it will attack here. With the elimination of chlorine, you will get this C double bond O, CH2, CH2. This. Now ethoxide ion, this nucleophile will attack here. Okay, you will get CO minus OC2H5, CH2, CH2. Now question arises, when it will come here, which bond, either this or this, then here both carbon positions, these two positions are quite equivalent, so the bond may break from either side, from this side or from this side. Suppose bond is breaking in this fashion, then it will be CH2 minus, I have written this, it is attached with this CH2 and it is attached with C double bond O, OC2H5. Okay. Now friends, if this bond breaks, negative charge will be here. Here these two positions are equivalent, quite equivalent. If these two positions are not equivalent, then you have to decide that which carbon ion will be more stable. And here ethyl alcohol is here, that ethyl alcohol will supply H plus here and you will get CH3, CH2, C double bond O, OC2, H5. It is ester. It means in favorskii rearrangement, when alpha halo ketone is heated with sodium methoxide and ethyl alcohol, we will get ester. Friends, number 17, it is quasi favorskii rearrangement. In favorskii rearrangement, we had seen that there is an alpha hydrogen to form carbon ion, but here there should be no alpha hydrogen. So when alpha haloketone having no alpha hydrogen, it is CH3, 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 C double bond O, C, PH, PH, Cl. It is alpha hydro. It is ketone. And it is alpha carbon, it is alpha carbon, where there is no hydrogen. Such ketone, alpha haloketone, is heated with sodium methoxide. What will happen? Here there is no chance to form carbon ion. So directly it will attack here in this fashion. And you will get CH3, 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 CO minus and OC2H5, and here it is C, PH, PH, Cl. You will get this. Now, when it will come here, what will happen? This whole unit will rearrange and it will come here. it will come here. Means this unit gets attached with this carbon. Means that carbon to which hydrogen is attached. So you will get, it is C double bond O, it is OC2H5, and it is attached with this carbon where there are two pH group, pH bond. This unit gets attached with this carbon. So right here CH3, CH3, CH3. It is ester group. Means also here you are getting ester like in favorskii rearrangement. Okay. Number 18. Shapiro rearrangement. When tosyl hydrogen, right, CH3, CH2, CH3, double bond N, NH, TS. When tosyl hydrogen is heated with base, that is butyl lithium, two equivalent, or it is organometallic compound which acts as base, any organometallic compound, and generally we use butyl lithium. When you see in any place butyl lithium and two equivalent, you should conclude that okay, it is Shapiro rearrangement. And what will happen? Two equivalent means 1:2. If one molecule of this, then you have to take two molecules of this. If it is 1 mole, you have to take 2 mole. So I have written two equivalent. This base actually Bu minus, it will take this hydrogen in first step and then after this hydrogen in second step. Okay. And here we will write both the abstraction of hydrogen simultaneously. CH3, CH2, CH2 minus, Li plus, and here N minus, TS, Li plus. Both the hydrogen atom, this hydrogen is acidic, this hydrogen is acidic, and one by one in two steps, these two hydrogen atoms, first this hydrogen and second this hydrogen, is abstracted by butyl anion, butyl carbanion. And here what will happen? First of all, it will come here, it will come here, it will come here. Okay, and then you will get CH3, CH2, C, double bond CH2. Okay, bond N, double bond N minus, and here this lithium ion and this tosyl ion is released like LITS. Okay, and Li plus is here. This is the situation. Now it will come here, it will come here. Okay, and you will get CH3, CH2, C, right, in this fashion, CH3, CH2, C minus, and it is double bond CH2. Okay, and nitrogen gas is eliminated. And here, now this carbon ion will take H plus from water. Suppose H2O is here, it will supply, it will act as electrophile, H plus, it will give H plus, and you will get CH3, CH2, CH double bond CH2. It is less alkylated or less substituted. This is ethylenic and there is one alkyl group attached with ethylene. So you are getting less alkylated alkane. So the statement will be when tosyl hydrazone is heated with 2 equivalent of butyl lithium, less alkylated alkane is formed. It is shapiro rearrangement. And shapiro rearrangement, I say it satir rearrangement. Why satir? When if you are taking water as electrophile, H will come here. If you will take RX, it will supply R plus. R will be here. R will be here. R will get attached with this carbon. And if D2 is taken, D will come here. Any electrophile, if present here, that electrophile gets attached with this carbon. That's why I call it satir rearrangement. Shapiro rearrangement is actually satir rearrangement. Okay. Number 19. Bomford Stevens rearrangement. When tosyl hydrazone, right here, CH3, CH2, C, CH3, double bond N, NHTS. When a tosyl hydrazone is heated with sodium ethoxide in presence of protic solvent or aprotic solvent, more alkylated alkene is formed. In shapiro rearrangement, you get less alkylated alkene, and in Bomford Stevens rearrangement, you will get more alkylated alkene. So we will see here mechanism of both the type. In presence of protic solvent, number 1, in presence of protic solvent, ethoxide ion will abstract this hydrogen, resulting in this CH3 double bond N, N minus TS. Now it will come here and you are getting it with the liberation of ethyl alcohol. Ethoxide ion will take this hydrogen with the elimination of ethyl alcohol, you will get this. Now minus TS minus will be liberated and you will get CH3, CH2, C, CH3 plus bond N, double bond N minus. Now it will come here and it will come here. Sorry, better to write here, friends. Lone perfluctan is here. This lone perfluctan will come here and this tosyl anion is released. Okay. Now here double bond is here and okay, plus charge will be here. Plus charge will be here. When it will come here, then it will come here. CH3 and right here ethyl alcohol, this ethyl alcohol. H plus will give this carbon ion. CH3, CH2, C minus, CH3, single bond N, positive charge and triple bond N. Okay. And ethyl alcohol will liberate H plus, that will come here. So right here H. You will get this. Now right here H, it will come here and this bond will break in this fashion and you will get more alkylated. You will get more alkylated alkene with the elimination of nitrogen gas. It is the mechanism in presence of protic solvent. Second mechanism of bomford disturbance rearrangement is in aprotic solvent. It is CH3, CH2, C, CH3, double bond, N, double bond, N, and positive charge is here and negative charge is here. We have taken the intermediate produced in first type of mechanism. We are going to start from here. Before this, in both the mechanism, steps are same. So, we are starting from this species. Okay. Now, it will come here and it will come here. In presence of decline or trigline, it is aprotic solvent. And you will get CH3, CH2, C, CH3 minus N plus triple bond N. Now, nitrogen gas is eliminated and you will get carbene CH3, CH2, C, CH3, right? In this fashion, bond C, bond C, bond N, double bond N, positive charge is here. Positive charge is here. Nitrogen is eliminated, so don't write this. Okay? Nitrogen gas is eliminated. You will get this bond CH3. It is carbene. Now, suppose right here hydrogen and this bond will break in this fashion. Then what will happen? One dot here, one dot here. Means one odd electron here, one odd electron here. This hydrogen, this H dot will combine with this carbon dot. CH3, CH, CH3. This hydrogen dot will combine with this carbon dot, and this carbon dot and this carbon dot will combine together, giving rise to double bond. Thus, you are getting more alkylated alkene in bomford disturbance rearrangement. Always people remember the difference in bomford disturbance rearrangement and shapiro rearrangement. In shapiro rearrangement, you are getting less alkylated alkene, and in bomford disturbance rearrangement, you are getting more alkylated alkene, and in both the places, reactants are same. That is tosyl hydrazone, and in both the places you use base. Here you use base. In bomford disturbance rearrangement you use base sodium ethoxide or sodium iodide, potassium iodide, sodium hydroxide, potassium hydroxide, etc. Number 20 is Fry's rearrangement. When phenyl ester, it is phenyl, C double bond O, OR. Friends, it is carboxylic acid. Suppose right here methyl, it is acetic acid. But in place of this, if you put, friends, not in this fashion but write it is O, C double bond O CH3. It is acetic acid. Sorry, it is acetic. CH3, C double bond O, bond H. If If in place of hydrogen you take phenyl, it will be phenyl ester. Right here, phenyl ester. Okay. When phenyl ester is heated with anhydrous aluminum chloride, you will get orthohydroxyestophenol and parahydroxyestophenol. Let us see its mechanism. Aluminum chloride is electron deficient compound, sextet in outermost orbit of aluminum here, so it is Lewis acid. It is Lewis acid. This lone pair of electron is coordinated to aluminum, and so you will get this O CS3 and here AlCl3, O here it is plus and here minus. Now this bond will break in this fashion and you will get Cl3Al minus O this and CH3 C double bond O positive charge. It is electrophile. Electrophile. Acetyl carbocation. Okay. Now it will come back. It will come back or right in this fashion. This electron is given to this and it will come here, negative charge will be here and it will attack here. If it comes here, negative charge will be here, then it will come at para position. So only I am showing the attacking of electrophile at ortho position minus AlCl3, again it is released, eliminated and you will get this. This COCS3 acyl group will be here. If H is here, it will come here, negative charge will be here and this H plus will come here and you will get this OH COCS3. If it is not here, it will be estophenol. If it is here, it is orthohydroxyestophenol. And in the similar fashion, this acyl group may attack here. When it will come here and it will come here, then it will come here, negative charge will be here and so acyl group will attack at para position. In this fashion you are getting the mixture of ortho and para isomer. Number 21. Baeyer Venkataraman rearrangement. When friends, it is acetophenol. It is acetophenol. And it is ortho acetoxy acetophenol. It is acetoxy. When it is heated with base beta diketone is obtained or 1,3-diketone is obtained. This base will first attract this hydrogen leading to this, right? C double bond O CH2 minus. Okay. O C double bond O CH3. It is carbon 9 and HB, H plus is extracted from here, HB is released. Okay. Now this carbon ion will attack here in this fashion. It is actually intramolecular claisen condensation. By claisen condensation you get ethyl acetate, remember. Now you will get this C double bond O CH2 O C CH3 O minus. Okay. Now when it will come here, it will come here. and you are getting right here this C double one O CH2 C double one O CH3 and O minus okay, O minus. And friends, when here Hb is released, when this Hb gives H plus, that H plus will come here. This will be the product and you are getting beta diketone. Number 22. It is claisen rearrangement. Friends, it is different from claisen condensation. In claisen condensation, you get ethyl ester state. Here, when allyl phenyl ether is heated, right here, CH2 CH double bond CH2. It is allyl group. Allyl, it is phenyl. When allyl phenyl ether, when allyl phenyl ether is heated, suppose it is isotopic carbon, what will happen? It will come here, it will come here, it will come here. So, you are getting here double bond O and here CH2 asterisk mark CH2 single bond CH double bond CH2. This and hydrogen is here. It will come here, it will come here and you will get this. You will get this. This H plus will come here because it acquires negative charge and so H plus will come here and CH2 double bond CH2. It is orthoallyl phenol. It is actually 3,3 sigma tropic rearrangement. It is 1, 2, 3 and it is 1, it is 2, it is 3. These 3 position gets attached with these 3 position. So it is called 3,3 sigma tropic rearrangement. Number 23. It is Cope rearrangement. Thermal isomerization of one 5-diene, 1, 2, 3, 4, 5. In is at 1 and 5. Thermal isomerization of 1 5-diene by 3,3 sigma tropic shift. 3,3 sigma tropic shift. Friends, it is 1, 2, 3. 1, 2, 3. 3, 3 gets attached here. Okay, this bond will break. It will come here, it will come here, it will come here, and you will get this bond is cleft. This, okay, methyl, okay. Double bond is here, double bond is here. This bond is formed. It is 1, 2, 3 position, and it is 1, 2, 3 position. 3, 3 position gets attached in this fashion. So it is called 3, 3 sigma tropic shift. So I have said 1 5-diene on isomerization, thermal isomerization gets, we will get this and it is called Cope rearrangement. In the similar fashion, you can see Aza Cope rearrangement. Right here 1, 2, 3, 4, 5, 6. One position, double bond is at one position, 1, 2, 3, 4, 5. It is fifth position. Double bond is at 1 and 5. 1, 2, 3. Okay. Right here R. Okay. And right here R dash. Okay. And suppose nitrogen is here 1, 2, 3, 4, 5, 6. Nitrogen is here. Nitrogen is, and here pH, phenyl group. Means 1, 2, 3 position. And here 1, 2, 3 position. Okay. This bond will collect. This bond will collect. Okay. It will come here. It will come here. And it will come here. Means this bond is collapsed. Okay. So first write this part. See R dash, double bond will be here. Nitrogen is here. Single bond. This nitrogen is here. And it is pH. It is pH. When this bond will come here, it gets attached here. Here. Because this bond comes here, positive charge will be here. So this bond will come here. Means this carbon gets attached with this nitrogen. This carbon. Then this carbon. Then this carbon. And double bond will be here. Double bond C. Double bond C. Double bond C. Okay. And with this carbon, double bond is here. With this carbon, it is R, it is R. This is age of rearrangement. 24 is bond richter rearrangement. It is aromatic nucleophilic substitution. Aromatic nucleophilic substitution. When aromatic nitro compound is heated with cyanide ion in presence of aqueous ethanol, this carboxylic acid is formed. And carboxylic acid, carboxyl group gets attached with the carbon that is just adjacent to nitro group. And so it is also called sign substitution. Sign substitution. Sign means adjacent. Adjacent. And Z is any group which is electron withdrawing group. Electron withdrawing group, due to presence of electron withdrawing group in benzene ring, rate of reaction is increased because this group will decrease the electron density of benzene ring. This nitro group is already electron withdrawing group. It also withdraws the electron of benzene ring, leading to decrease in electron density of the ring, and overall there is much decrease of electron density of benzene ring, and it leads to attacking of cyanide ion. Due to presence of electron withdrawing group, electron density of benzene ring is decreased, and cyanide group will attack frequently. Dhakadhak. Nucleophile will attack at electron deficient species. Now we will see its mechanism. Okay. And here it is N double bond O minus N plus. Cyanide ion. It is cyanide ion. It will attack here. It will come here. It will come here. So you will get this, that n minus double bond will be here, and it is C triple bond N, C triple bond N, H is here, it will come, okay, and it is positive charge and it is minus. Now it will come here, it will come here, and it will come here, it will come here. So you will get this Z N O minus, it is positive charge, double bond O, double bond O, C double bond N minus this. Sorry, it will come here and there will be no positive charge, and here single bond, and minus this electron will come here. So it is the situation. Friends, when this bond will shift here, H plus will be liberated, and here it is minus charge, so hydrogen will come here. Okay. Now this electron, it will come here and it will come here and it will come here. So situation is this, structure is this. It is Z, it is N double bond O, this double bond O, I am writing in right side, okay, because this bond is cleft and this oxygen fully gets attached with this carbon, so it is C double bond O NH, minus charge will be here, NH2 right here, minus charge will be here, and H plus, when minus charge is here, H plus will come here, and H plus comes from water, H2O. When H plus will come here, hydroxide ion will be liberated. Okay, this is the situation, and here this oxygen and hydrogen will combine together, giving rise to this Z N double bond N C double bond O, this. Now water gives H plus, which gets attached here, and hydroxide ion is liberated. Now that hydroxide ion will attack at this carbon, and this bond will break in this fashion. When hydroxide ion attacks at this carbon, what would you get? It is Z, it is N double bond N C, OH will get attached here and it is O minus. Now when it comes here, it will come here and it will come here. It will come here. Then negative charge will be here, okay? And H plus from water will come here because negative charge is here. And hydrogen, this H plus will come here, and this is nitrogen gas is eliminated, and here it is Z, and here COH double bond O. You will get this. It is carboxylic acid. So friend, it is all about the mechanism. Here you have only to understand that, remember that carboxyl group gets attached with the carbon which is adjacent to the nitro group. It is 25th sommelet hauser rearrangement. It is also aromatic nucleophilic substitution. Friends, one thing you have to remember that von Richter rearrangement, sommelet hauser rearrangement, and next I will teach you Smith's rearrangement, VSS. These three rearrangements are very, very important for NET, GATE, IIT JAM, and all the three rearrangements are aromatic nucleophilic substitution. VSS, remember it, VSS. Sommelet hauser rearrangement. When benzyl, it is benzyl trimethyl ammonium halide is heated with sodamide, NaNH2, strong base. NH2 minus is a strong base, right here, a strong base. You will get this CH3 and at ortho quotient. Friends, this part will come here. This part will come here. And moreover, this nitrogen does not get attached here. Rather, this methyl group, one methyl group is here, CH2, then NMe2. It will be your. Now, mechanism. Write this. It is CH2 and CH3 Me2 plus X minus. Don't write it, only this. Okay. Now, base is here, which is NH2 minus, strong base. It will abstract this hydrogen, leading to carbon ion. CH minus bond N plus Me2 and CH3. You will get this carbon ion. Friends, this carbon ion will change into this carbon ion. Negative charge will be here. Here CH2 and Me2 plus CH2 minus. It is less stable and it is more stable. Even then, it changes into this due to a certain purpose, and purpose is this, that it will attack here, it will come here, and it will come here. Purpose is this, and due to this, due to formation, due to attacking of this, rate of reaction proceeds ahead, and Le-Chatelier principle will be applicable here. So you will get here this double bond CH2 and here CH2 and Me2. and hydrogen is here. Now it will come here, it will come here, and you will get CH3, CH2, and Me2. This is all about sommelet hauser rearrangement. Number 26, Ismail's rearrangement. It is also aromatic nucleophilic substitution. Okay, friends, again I am repeating VSS, Baumeister, sommelet hauser and Ismail's. These three rearrangements are aromatic nucleophilic substitution and very, very important for the purpose of examination related to GET, IIT JEM, NET, etc. Here it is Z, electron withdrawing group, and it is X, and it is Y. Here it is this Y is either, this Y will contain either lone pair of electron or negative charge, means it should be nucleophilic in nature. And here X may be SO2, S, SO2, S, SO, etc. And Y may be OH, NH2, and so on. Either negative charge should be there or lone pair of electron should be there, C and this. Okay, and Z is electron withdrawing group, and it is base is here, and it is actually intramolecular rearrangement. Actually this will attack here, and the product is, it is Z, and it is here it is X, but here it is Y, and here X. This will be your product in Ismail's rearrangement. Now we will see its mechanism. This. Okay. Okay. It is Z. It is X. It is YH. Okay. Base is here. This base will abstract this hydrogen. This hydrogen Z. And here X, Y minus. Now it will attack, it is nucleophile, it is the intramolecular. It will attach intramolecular nucleophilic attack. It will attack here, and what will happen? This bond will come here. So it is Z, negative charge will be here, X, Y, and it gets attached with this carbon. Okay. Now it will come here, it will come here, it will come here, and it will come here, and so you will find this double bond will be here, double bond here, double bond here. It is Z, it is X, it is X. This gets attached with this, so it will be Y, Y, it will be Y. With Y it is this carbon, and with this it is this carbon, and with this carbon it is X. So right here X minus. This will be the product, and it is all about Smiles's rearrangement. Friends, now I stop my lecture, and we have seen 26 rearrangements here in one lecture. So I have given the heading pattern of this lecture, revise 26 rearrangements. Although I have uploaded these rearrangements separately and in detail, but for the examination point of view, for the revision, I have formed an important lecture in about 19 minutes, 1.5 hours. You can revise all the 26 rearrangements, which are very much important for BSc, MSc, IIT, JAM, NET, GET, etc. So I request you revise this lecture daily up to 1 week. Then randomly, then now and then you may revise, but before the examination, 1 day before the examination, you have to revise, you have to see, you have to watch this video. Hope you will like this video. I have labored hard. So friends, I think must you will comment. How do you feel? How do you think about this lecture? Thank you. Thank you. Thank you very much.